Here's an interesting problem. How do you create a delayed duplicate of a sound without recording it to some sort of storage medium?
Back in the days before computerized audio processing and cheap abundant memory, this was a prime engineering issue. That's because at that time, the only practical electronic implementation of an audio delay effect was large, bulky tape echo machines.
These machines worked by recording an input signal to electromagnetic tape and then playing it back with a time delta. Of course, you could always decide to go no-tech and use a wide open space with a reflective surface in the distance to create an echo.
This works because it takes time for sound to travel through a medium such as air.
In the late 60s, two electrical engineers named Sangster and Teer managed to implement an idea that was essentially a unique hybrid of the two concepts I just mentioned, the bucket-brigade delay. This circuit first splits an audio signal into analog samples, which are then routed sequentially through a chain of transistors and capacitors, similar to how sound travels through a medium. At the output, the signal is reconstructed from those samples. And because passing the samples along the transistor-capacitor chain takes time, the reconstructed signal will be delayed compared to the input, with the length of the chain determining the total delay time.
In this video, I want to reverse engineer the architecture of a classic bucket-brigade delay, recreate a bare-bones version on the breadboard, and then use a proper BBD chip to implement a simple audio delay effect.
We'll start by investigating the first stage of a BBD, the analog sampling subcircuit, which splits the input into transmissible chunks. Okay, but what does that mean exactly? Well, in electronic circuits, an audio signal is represented as a swinging voltage, like this triangle wave. To extract a sample from this means that we probe the signal at any point and store whatever value we read. If we do this continuously and in regular intervals, we get a series of samples that resembles the input. But unlike a swinging voltage, those samples are discrete and can be easily held in a capacitor, allowing us to control when and how they move through the rest of the circuit. Alright, so how do we extract a sample from a signal? All we need are two components: a field effect transistor, FET for short, which will act as a probe, and a capacitor, which will act as a storage medium. The transistor has to be a FET because, unlike bipolar junction transistors, FETs allow for bidirectional switching. This is important because depending on the state of the input waveform when we probe it, current might need to flow into or out of our sampling capacitor.
But while BBD chips normally use MOSFETs, we'll use a JFET as a substitute, since discrete standalone MOSFETs are unfortunately built in a way that disqualifies them for bidirectional switching.
To understand how the sampling process works, let's first assume that our input is a static 1-volt signal. Then, to sample that signal, we activate the JFET by bringing its gate voltage close to the source voltage. This allows current to flow into the capacitor until the voltage above it is 1 volt as well. Next, we pull the gate voltage way below the source, disabling the JFET. This cuts the connection between signal and capacitor, which means that the charge is now trapped inside the cap. This trapped charge is our sample. Okay, but what about a non-static signal? Luckily, it works just the same. We activate the transistor by raising the gate voltage, which causes the voltage above the capacitor to follow the input. Then, we pull the gate voltage low to trap a sample inside the cap.
This works because while the transistor is open, charge can freely flow into and out of the capacitor as the input signal oscillates.
At least if it stays within these limits, which are determined by the gate voltage we use to activate the transistor and its gate-to-source threshold. If the input crosses the upper line, the transistor will close, since the gate is too negative compared to the source. And if it crosses the lower line, current will flow into the gate, potentially damaging the transistor. This is an issue because audio signals normally swing way outside these limits. So if we want to test our sampling circuit in practice, we'll need to scale and bias whatever input we want to feed it. For that, we can use a simple inverting op-amp, which will give both the input signal and an offset voltage. By balancing the input resistances against the feedback resistor, we can determine the exact amount of scaling and biasing we want to apply. Since I plan to use audio from my Eurorack synthesizer as our input, we can assume that input to be a 10 volts peak-to-peak signal that swings across the 0 volts line. In that case, these resistor values will give us an approximately 1 volt peak-to-peak result that is swinging just above the 0 volts line. Okay, so with our input signal sorted, the next step is figuring out how to control when each sample is captured.
As I said before, this needs to happen continuously and in regular intervals, so that all of the samples taken together resemble the input. Frequency is also a consideration here, since it will determine the sampling resolution.
And the higher the sampling resolution, the more accurately the samples will resemble the input. So we'll want to automate the sampling process with a fast clock signal. Essentially, just a high-frequency square wave swinging between 0 and -5 volts. And while we could generate this clock with any basic square wave oscillator, I'm going to use a 4046 phase-locked loop chip instead. And that's because the 4046 contains a full-blown VCO, which is an oscillator that allows us to control its frequency with a voltage. This will become important later in the video. To use the VCO inside the chip, we first need to supply it with power. Since we want our clock to oscillate between 0 and -5 volts, we'll give it 0 volts as a high and -5 volts as a low supply voltage. Next, we'll set the oscillator's frequency range. If we combine a 39K resistor to the negative supply at pin 11 with a 1 nanofarad capacitor between pin 6 and 7, the VCO can produce clocks between 0 Hz and around 27 kHz. Because it doesn't really make sense to have the frequency go down to 0, we'll add a frequency offset of around 800 Hz by connecting pin 12 to the negative rail via a big 2.2 megaohms resistor. Next, we'll need to apply a control voltage to pin 9. For now, we'll simply set up a 100K potentiometer as a variable voltage divider between -5 and 0 volts. Since the 4046 has a CV input dead zone of about 1 volt above the lower supply, we'll also insert a 22K resistor between the pot and -5 volts, limiting the divider's minimum output to around -4 volts. Finally, we'll start the oscillator by tying pin 5 to the low-level supply.
To test our sampling stage in practice, I'm going to use Labor, which is a synthesizer prototyping tool I developed in collaboration with Erica Synths.
It comes equipped with everything we need to set up our circuit: a Eurorack power supply, a free-running multi-waveform oscillator, a variable voltage source, and a modular interfacing section for jack sockets, switches, and potentiometers.
If you want to follow along, both Labor and a DIY BBD kit with all the necessary components are now available in the Erica Synths webshop. Links are in the description.
Okay, to start off, I'm feeding Labor's sine wave oscillator into our scaling and biasing subcircuit, before routing it to a J113 JFET followed by a 1 nanofarad capacitor. Then I've connected the clock generator, which receives its -5 volts supply from Labor's variable voltage source, to the JFET's gate. On the oscilloscope, we can see that the capacitor voltage looks like a sine wave, but with strange jagged edges. What's up with that? Simple. When the transistor is active, the cap voltage follows the input voltage. And that's why those parts are rounded. This is the sampling phase. And when the transistor is disabled, the cap voltage stays locked to the last value, resulting in visible stair steps. These are our samples. Now, if I increase the clock frequency, you can see how those jagged edges become smaller and smaller. That's because we're increasing the resolution of our sampling process, giving us an output that resembles the input sine wave much more closely.
Great! Now that we've split our signal into samples, we can think about achieving the delay effect itself.
The trick here is to take the individual samples and move them through a chain of containers, synchronized with a clock signal. Since each transfer from one container to the next takes a small amount of time, 1 clock wave cycle to be precise, the samples will reach the end of the chain with a time delay relative to the input. That time delay depends on the number of transfers and the frequency of the clock. If we then reconstruct the waveform from those delayed samples, we should get an output wave that's been shifted forwards on the x-axis, or in time. Alright, but how exactly do you transfer a sample? Well, in principle, if you have one capacitor that holds a sample on the left, and an identical but empty capacitor on the right, you just need to move the charge from cap 1 to cap 2 in response to a clock pulse. You might assume that we can do this with another JFET. Plug it in between the two caps, connect our clock to the gate, and then the JFET should allow current to flow from cap 1 to cap 2 when the clock goes high. The problem with this idea is that we need all of the charge to move, but only half of it will. Because then the voltages on both sides of the transistor will be equal, causing the current flow to stop.
This is the exact issue that Sangster and Teer were faced with when they first developed the bucket brigade delay in the late 60s. The solution they came up with is simple, but not obvious at all. Instead of transferring charge between capacitors, they decided to transfer the charge deficit. It works like this.
We first add another JFET, which we connect to capacitor 2 on the left and a 5 volts voltage source on the right. Then we connect the other side of capacitor 2 to the gate of the first JFET, instead of connecting it to ground. Next, we'll open JFET 2 by grounding its gate, while keeping JFET 1 closed with a low gate voltage. This allows current to flow into capacitor 2 until we hit the JFET's gate-to-source threshold. Assuming that threshold is -2 volts, the current flow will stop once we read 2 volts above the cap. Keep in mind that this is relative to ground. If we measured the voltage across the cap, we'd see 7 volts instead. Next, we close JFET 2 by pulling its gate voltage low, and we open JFET 1 by pushing its gate voltage up. This also applies force to cap 2, causing current to flow from right to left until cap 1 hits the gate source threshold at 2 volts. In this process, cap 2 loses exactly as much charge as cap 1 was missing relative to the 2 volts maximum, 1 volt in this specific case. This is why Sangster and Teer call this technique a charge deficit transfer. The deficit has moved from cap 1, which is now full, to cap 2, which is now missing 1 volt. And because we give cap 2 a strong push from below via the preceding JFET's gate voltage, this will work even if cap 1 starts out completely empty.
Of course, this doesn't just work for a single transfer. We can add an arbitrary amount of JFETs and capacitors all set up in the same way to increase the number of transfers.
Charge will flow from right to left in just the same way, while the deficit travels from left to right until it reaches the end of the chain. Note that to automate this circuit's operation, we'll need a second clock signal that is the exact inverse of our existing clock to drive every other JFET. Also note that each cap is only carrying information on every other clock pulse. It is either full, which means it's not carrying information, or at a charge deficit, which means that it is carrying information. Next, we'll want to combine the charge deficit transfer idea with our previously established sampling stage. All we have to do there is add the sampling JFET and capacitor back in at the beginning of the chain and connect the JFET's gate to clock 1. Then during the sampling phase, when clock 1 is high and clock 2 is low, JFET 2 will be closed, isolating the sampling stage and allowing it to operate just as we discussed earlier. And when the clocks flip, JFET 1 will be closed, kicking off the deficit transfer process.
Before we can try this, we'll need to modify our clock circuit so that it generates an additional inverted clock. Thankfully, we don't have to bring in any extra components for this.
Because if we tie pin 14 on the 4046 chip to the high-level supply, pins 2 and 3 act as a simple inverter, with pin 3 as the input and pin 2 as the output. So if we connect the original clock to pin 3, we can pick up our inverted clock from pin 2. On the breadboard, I've added 3 BBD stages to our existing circuit. For the input, I'm using the same scaled and biased sine wave from before. On the oscilloscope, I'm monitoring the voltage above the final capacitor in the chain. As expected, that voltage alternates between the full state, 2 volts relative to ground, which carries no information, and the deficit state, 5 to 6 volts, which is moving up and down in a sinusoidal pattern. This is our sampled and delayed input.
Now, in order to hear how it sounds, we need to add a voltage buffer to avoid drawing current from the capacitor and distorting the signal. And while we could use an op-amp here, BBD chips typically use a MOSFET for a smaller footprint.
Lucky for us, we can actually do the same. And that's because voltage buffering is a unidirectional use case, which works just fine with a discrete MOSFET. The core mechanism is very much comparable to a regular BJT emitter follower. The signal we apply to the MOSFET's gate is reproduced above the source resistor due to negative feedback. There are 2 important differences, though. First, a MOSFET's gate terminal is isolated from the rest of the device, meaning that it doesn't draw constant current from the signal we're trying to replicate. And second, a MOSFET's activation threshold can be much higher than that of a standard BJT. Both of these things are great in our use case because 1, it's important that we do not draw current from our BBD stage capacitor. And 2, a high activation threshold means that we can reproduce the output signal with the same 5 volts supply voltage we used to fill up the capacitors. The latter needs a little bit of an explanation. If we take a look at our current output signal, you'll notice that the deficit states are all above the 5 volts line. If we tried to buffer this with a standard BJT emitter follower and a 5 volts supply, everything above around 5.6 volts would be cut off. And that's because the activation threshold for a BJT is around 600 millivolts, which means that the voltage drop between base and emitter is 600 millivolts as well, shifting the output downwards by that amount and allowing us to buffer an input that's going slightly above our 5 volt supply voltage. With a MOSFET, that threshold can be considerably higher, depending on the model. And a higher threshold means that the output will be shifted downwards quite a bit more, giving us considerably more headroom with the same 5 volts supply. Granted, this is not super important on the breadboard. We have a 12 volts supply available after all. But for a BBD chip, it would be pretty inconvenient to require 2 separate supply voltages just so we can buffer the output. To test this, I've set up a 2N7000 MOSFET as a voltage buffer over here. As you can see on the oscilloscope, it seems to be replicating our chain's output just fine. So let's listen to it by routing it through Labor's output amplifier. Interestingly, we can hear both the sine wave and the clock in the output, with the latter being significantly louder in the mix.
This makes sense, unfortunately. Our signal is oscillating between the full state and the deficit state at the exact rate of the clock signal, which is why that clock signal is so prominent in the output.
Bummer. How do we fix this? Lucky for us, there is a classic BBD trick we can apply. Dual tap signal reconstruction. If we compare the signal at capacitor 4 to the signal at capacitor 3, you'll notice that they're complementary in the sense that whenever cap 4 carries no information, cap 3 does, and vice versa. If we were to combine the two, we should be able to cancel out the clock oscillation, since the signal wouldn't jump between full and deficit state anymore. To test this, we'll simply set up another MOSFET buffer for cap 3 and then mix its output with the previous buffer using a simple passive mixer made of two 10K resistors. Since the reconstructed wave will have a significant DC offset, we'll then AC couple it using a 1 microfarad capacitor and a 100K resistor to ground. Finally, we'll add an op-amp set up as a non-inverting buffer for a low output impedance. On the oscilloscope, we're now looking at the op-amp's output. Let's hear how it sounds. While the amount of clock noise is definitely reduced, it does still have a lot of whine in it. This is because, first, the two signals are not perfectly complementary, so there is no clean handoff between samples. Instead, we see these brief transitions from sample to full state and back. And second, the samples themselves also contain a clock spike, because the charge deficit transfer is not instantaneous. So what we're seeing here is one capacitor discharging into the previous one until the deficit is fully transferred.
To try and deal with this, BBD circuits usually apply an aggressive low-pass filter to the output.
To see how that would improve things, we can add a 10 nanofarads capacitor to ground after our two resistors, creating a basic low-pass filter. Of course, this cuts away parts of the signal, but that's usually par for the course for a BBD. It's where they get their characteristic dark tone. As expected, the output waveform now looks and sounds a little cleaner. I'm not super happy with it, but we'll get back to this later. Because at the moment, our circuit is still pretty useless as a delay, since 3 transfers at a clock frequency of 10 kHz gives us an effective delay time of just 300 microseconds. So if we overlay our input and the delayed output, we see just a very small shift on the x-axis. We can of course try to increase the delay time by reducing the clock speed. But since that clock controls both the transfer process and the sampling process, the more we reduce the clock speed, the worse our sampling resolution gets.
Since we can only drop the clock speed so much before the output becomes completely unrecognizable, we should focus on a different strategy to increase the delay time instead, adding more stages to the chain. But because useful delay times at reasonable sampling rates can only be achieved with hundreds, if not thousands of stages, it's not feasible to set this up on our breadboard using discrete components.
Instead, we'll use a dedicated BBD chip, the V3205, which implements pretty much the same architecture we have just set up, but with 4096 stages instead of just 3. There are 2 slight differences that will require us to make changes to our existing circuit though. First, where we use JFETs, the chip exclusively uses MOSFETs. Because remember, non-discrete MOSFETs can actually be used for bidirectional switching. Since those MOSFETs are closed at 0 and open at 5 volts gate voltage, we need to adjust our clocks to alternate between those values instead of 0 and -5 volts. To get there, all we need to do is feed our 4046 clock circuit 5 volts as its high level and 0 volts as its low level supply.
Additionally, we'll also need to adjust our input signal's bias and scale, since the MOSFETs in the V3205 operate with different gate-to-source thresholds than our JFETs. In my experiments, the chip only responded well to signals swinging between around 1.9 and 3.2 volts. Anything above and below will be cut off.
To move our input into that range, we'll first replace the 200K offset resistor with a 47K. This will increase our offset by around 2 volts. Next, we'll have to reduce the input resistance to increase the output's gain and make use of the available headroom. Because we might want to send in signals that are lower in volume than the Eurorack standard 10 volts peak to peak, we'll drop that resistance down to 51K. And then insert a 100K variable voltage divider between it and the signal. This way, we can dial in the appropriate input gain for a wide range of signals, instead of just fixing it to a value that only works for a specific type. Okay, now the other difference between the chip and our JFET implementation is that the chip seemingly adds another transistor to each stage, whose gate is connected to a voltage labeled VGG. But this is actually just a tricky detail of how the individual delay stage MOSFETs are manufactured. Sangster refers to this as a tetrode MOS structure, a single MOSFET with 2 gate terminals. By applying the clock to one of them, as we were, and providing the other with a high-level voltage that is close to the supply, 14/15 of the supply to be precise, the MOSFET's ability to transfer charge is improved.
I won't pretend I understand how this works in detail, but this refinement ensures that the charge deficit is always completely transferred with minimal error, which ultimately means less distortion in our output.
To test all this, here's how we'll set up the V3205. First, it needs to be supplied with 5 volts at pin 5 and ground at pin 1. Next, we'll give it the VGG voltage at pin 8 via a 4K7 56K voltage divider between 5 volts and ground. Then we'll send clock 1 into pin 6, clock 2 into pin 2, and our scaled and biased input into pin 7. Finally, we'll drive our output reconstruction circuit from pins 3 and 4. As expected, we're still getting a reasonably clean sine wave out of our circuit. Now, let's see what happens if I turn down the clock frequency. Looks like the added stages allow us to significantly push the output back on the x-axis. Great. Though I'm really not happy with the amount of clock noise bleeding through, even with the low-pass filter. Traditionally, the way to fix this has been to use a low pass with a much steeper slope than ours. This way, more of the annoying clock whine is cut out, but also more of the input signal's upper frequency range.
And depending on how low we want our clock frequency to go, this would be a significant chunk. To avoid this, I want to go with a different solution that does not involve filtering.
To get there, let's go back to the raw, unmixed and unfiltered output from our BBD chain and compare it to the ideal clean output that we're aiming for. You'll notice that where our actual output jumps between different voltage levels, the ideal output sticks to the same voltage for an entire clock cycle. That voltage is the sample we took at the BBD's input. And we get that voltage in our actual output between the initial spike and the mid-clock cycle drop. So if we were to grab a small sample somewhere in this area and then hold that value until we grab the next one, we should be able to extract our ideal signal from the noisy BBD output. To try and implement this idea, we'll first need to undo our mixing and filtering approach. This means removing one output from the equation and killing the basic low-pass filter. However, we'll keep both the AC coupling and the buffer to ensure that we don't run into any headroom issues later on. Next, we'll set up a general-purpose sample and hold circuit. You can check one of my previous videos for an in-depth explanation, but there are 3 main differences compared to the sampling circuit we set up in the beginning of this video. First, there is an added 100K resistor between the input and the JFET's gate terminal, plus a diode between the gate and the sampling trigger. This removes the need for biasing and scaling the input by ensuring that the gate is always locked to the source voltage during the sampling phase, which is very useful since we don't have to worry about what the signal coming out of the BBD chip looks like. We'll be able to sample it without rebiasing or rescaling, at the expense of a more complex circuit. Second, there is a gate-to-trigger converter between the clock and the diode at the JFET's gate. This turns the square wave clock into a super narrow pulse, giving us a very short sampling window.
But not only that. Additionally, that gate-to-trigger converter will provide us with something called a propagation delay.
This means that there is always a very small time difference between the clock going high at the input and a trigger being generated at the output. This shifts the trigger pulse to the right ever so slightly, allowing us to dodge the worst part of the clock spike. Okay, but our sampling window still contains a sizable chunk of that spike. Wouldn't this show up in the output? It would if charging and discharging the sampling capacitor was instantaneous. But depending on the size of that capacitor, charging and discharging it takes a considerable amount of time. So by picking a relatively big capacitor in our sample and hold, we'll get more of a rough average voltage than a one-to-one reproduction of this downward slope. Third and finally, there is a non-inverting amplifier at the output with a gain of around 5. Restoring the signal to standard Eurorag levels, plus another round of AC coupling to remove any remaining DC offset from the reconstructed signal. To see how all this works in practice, we'll first compare the gate-to-trigger converter's output to the clock signal. And indeed, there is a clear gap between the clock's rising edge and the generated trigger. So if we now swap the clock signal for the BBD chip's output, the trigger is dodging the worst part of the spike as expected. And in combination with the big sampling capacitor, this produces an output that is surprisingly clean. For comparison, here's how it looks with a smaller 1 nanofarad sampling cap. The spikes are bleeding through very clearly. So back to the 10 nanofarads capacitor. To hear how it sounds, I'll switch our static waveform for a proper synth sequence. As I reduce the clock speed, you can hear the effect of the lower sampling rate, giving the sound a crunchy digital feel. You'll also notice that we're getting that typical re-pitching effect as I turn the clock frequency knob. This happens because changing the clock speed alters the playback speed for the samples that are already inside the chip. While those samples are being played back, the pitch changes according to the new playback speed. And once that string of samples has reached the end of the transistor capacitor chain, the pitch returns to normal as the sampling and playback speeds realign. Cool. Now let's compare our solution to the traditional BBD technique of dual tap reconstruction plus low-pass filtering.
For me, the difference is night and day. The reconstruction sampling approach gets rid of the clock noise almost entirely, while the traditional approach still has lots of noise, plus a much more muffled sound.
Great, but so far, we're only getting what you would call a fully wet signal from our circuit, meaning that we only hear the delayed sound, not the original one. To change this, we'll add a simple dry-wet mixing stage. We'll start by sending the wet and dry signals to opposite sides of a 100K potentiometer. Then we'll buffer the signal at the pot swiper with a simple op-amp buffer. This way, we've created an active mixer that allows us to apply different weights to both inputs simultaneously by turning a knob. Because we now draw current from our input in 2 separate places, I'm also going to buffer it, just to make sure we don't load the signal down and potentially distort it. Right now, I've turned the potentiometer all the way clockwise, so we only hear the wet signal. Let's see what happens if I move it in the other direction. As expected, more and more of the dry signal comes in until the wet version completely disappears. Great.
So far, so good. What we have now is what's commonly known as a slapback delay, a single delayed repeat. But what if we want multiple repeats instead of just one?
Thankfully, getting there is really easy. All we have to do is feed the wet signal back into the input via the scaling and biasing op-amp. Because then, every repeat will go through the BBD chip again and again. Using an 82K input resistor here will give us a feedback gain of about 1, which would result in an infinite number of repeats. The circuit basically goes into self-oscillation. To be able to dial this back, we'll put a 10K potentiometer as a variable voltage divider between the wet output and the 82K resistor. Small side note, but since the feedback potentiometer is providing a path to ground, we can get rid of the 10K AC coupling resistor at the wet output. It's simply redundant now. Sounds like this is working as expected. I can vary the number of repeats from just 1 to so many that the chip goes into wild self-oscillation mode. Cool.
But while our current delay time range is working great for, well, delay, I would like to be able to push it up into flanger territory. A flanger, if you don't know, is basically just a delay with a super short delay time.
Since the delay time depends on the speed of our clock, we can shorten it by increasing the clock frequency. For that, all we have to do is swap the 1 nanofarad capacitor for a smaller one. A 220 picofarads replacement gives us a frequency range of around 4 kHz to 112 kHz, which should result in delay times ranging from around 1 second to just 35 milliseconds. And because I'd like to jump between delay and flanger mode on the fly, I'll set up both capacitor options behind a simple SPDT switch. As expected, we can now get much shorter delay times, which, with a bit of feedback, start to sound really trippy. Great, but you might ask, why not use an even smaller capacitor for even shorter delay times? To answer that, let's take another look at the triggers driving our reconstruction sample and hold circuit compared to the BBD chip's output. Right now, the clock frequency is dialed to a rather low rate, but watch what happens as I turn it up. The parts of the output signal that actually carry the samples get smaller and smaller, until they're almost smaller than the sampling window itself. If they were to become smaller than the sampling window, we'd end up with severe distortion in the output. So the 220 picofarads capacitor is actually the perfect choice here.
Now, an actual flanger is not just a delay with a super short delay time. It also modulates that delay time using an LFO or similar. That modulation gives it that characteristic jet plane sound.
To implement this in our circuit, we'll need to add a control voltage input for the clock frequency. And this is why I went for a 4046 based clock generator in the first place. We're already controlling it using a voltage. We just need to find a way to mix that voltage with an additional external voltage. The naive approach here would be to use 200K resistors as a simple passive mixer, which would work in principle, but in practice, this would create a rather annoying usability issue. And that's because a passive mixer doesn't produce the sum, but rather the average of its input signals. Imagine we've got our delay time potentiometer dialed all the way up, causing it to send out a 5V signal. If we now add an external signal that's currently idling at 0 volts, you'd expect the delay time to stay the same. 0 volts should mean that no modulation is applied. But since our passive mixer is producing the average of our two input signals, the resulting control voltage would drop down to 2.5 volts, causing the delay time to drop down as well.
Bummer. How do we fix this? Well, normally you'd have to go through the trouble of adding a full-blown summing mixer involving 2 op-amps and a couple additional resistors. But in our case, there is a clever trick we can apply.
If we modify the variable voltage divider to double its maximum output voltage, adding in the 0 volts external voltage actually scales the knob's range down back to the original 1 to 5 volts. We're essentially first multiplying and then dividing by 2. Okay, but what if there is no external signal plugged in at all? In that case, we would blast the 4046's CV input with 10 volts, which it is not able to handle. To fix this, we'll simply add another variable voltage divider before the external CV input. This solves two problems at once. First, it provides a path to ground even if there's no external signal plugged in. And second, it allows us to change the intensity with which the CV affects the delay time. There's one small issue left. What if the external CV is going above 5 or below 0 volts? In that case, we might again apply voltages to the chip that it is not able to handle. To prevent that, we'll make use of diode-based limiting. If we simply add in 2 diodes after our mixer, one pointing up to the 5 volts rail and one pointing up from ground, then the voltage at the chip's input can never go significantly above 5 or below 0 volts. That's because if it tries to, the diodes conduct and thereby neutralize the unwanted in or decrease. To test this, I'll first sweep the delay time knob's range without any external CV applied. As expected, the range stayed roughly the same. Next, let's connect Labor's oscillator to the clock CV input. And yeah, I'm able to dial in different amounts of modulation going from subtle to extreme. Great. And while our circuit is now pretty much feature complete, there is a pin on the 4046 chip that caught my attention, the Inhibit pin, which we've decided to tie straight to ground previously. As a reminder, the voltage applied to that pin decides whether the chip's oscillator is running or not. So if we were to expose that pin via a jack socket, we should be able to start and stop our delay using a control voltage. To protect the pin from voltages below 0 or above 5 volts, we can repurpose the diode-based limiting approach that we just came up with. And yeah, this allows us to create a fun rhythmic stuttering effect. Great. With this final addition done, here's a bunch of example patches to showcase what you can do with the circuit. And with that, we've created a great sounding delay and flanger in a pretty compact circuit. If you decide to build this for yourself, I'd love to hear how it went. Let me know in the comments. Feel free to share any ideas for improving the circuit too.
If you'd like to support the channel, consider joining my Patreon or checking out the lineup of Eurorack DIY kits I develop in collaboration with EricaSense. You can get most of my designs as complete bundles with components, a PCB, panel, and an in-depth user manual in the EricaSense webshop. The BBD kit for following along with this video is now available too. You can find links for all of these things in the description.
Anyway, thanks for watching, and until next time, see ya.